Welcome back to Programming with Python. Today's lecture is about data structures that go beyond the basic data types that we have discussed so far. If you recall, we have learned about integers, floating point numbers, Boolean values, and also strings. But we haven't been able to store more than one object within a single variables. And that's what so-called compound data types are for. Lists are the most common data structure available in Python, and as the name suggests, a list is simply a list of values where each element has an index which in Python starts counting at 0. Okay, so it's a zero-based indexed collection of items. Now, the way we define lists in Python is with square brackets, as is shown here, and maybe it's easiest to just demonstrate you a few things directly in Spider. So I'm gonna define my list X, and as you can see, the definition simply starts with a square bracket. Then we list our elements separated by commas, and then we have a closing square bracket indicating that this is the end of the definition of a list. When I run this file, I can see in my variable explorer that the variable x is of type list and it has 5 elements, and we can even read off the value here. Of course, I can also output the list directly here in the IPython console. Okay, so it's very easy to define lists, and the nice thing in Python is that you're really not restricted to lists of only one data type. You can actually have integers, floating point numbers, strings, and let's say a Boolean value all in one list, okay, without any problem. Okay, so it's perfectly fine to mix different data types in a list. This is different from some other programming languages that you might have heard of. Now, we have defined this list, which now has 8 elements. How can we access the entries? Well, that's done by, again, using square brackets. So we type the variable name, which in this case is x, followed by square brackets, and now we can enter an index here. For example, index 5. And this would now address an element in our list with index 5, and we need to be careful which element we mean, because counting of the indices starts at 0. So 17 is our element with index 0. This has index 1, 2, 3, 4, 5. So x5 should refer to this floating point number listed here. So let's output x5 to the console just to verify that. And indeed we see here that we have addressed the correct element. The first element in our list is x0. It is also possible to address elements counting from the back of the list by using negative indices. So the element with negative index -1 is the last entry in our list, which is in this case the Boolean value false. Now, it is perfectly valid in Python to define a list that has no elements, the so-called empty list, and that's simply done as I've indicated here. You have square brackets without any elements. And we can verify that x is now a variable that is of type list, and it has size 0 because we have 0 elements. It is sometimes preferred to be more explicit in the notation using the list function available in Python. So this here is completely equivalent. It would also create an empty list, but it is in a sense more explicit in the code. It clearly states that we are defining a list here, which sometimes is helpful when we want to make our code as clear as possible. The fact that list is a built-in Python function, of course, tells us that we should also not use the word list as a variable name. Now, let me copy and paste a slightly more interesting list from the lecture notes to Spider. Here is a list X with 10 elements. I would like to now demonstrate the use of the slice operator, which is the colon in Python. Okay. With the colon, we can extract multiple elements from a list as follows. Let's say I want to extract the elements with index 2, which would be 23 here, up to the end of the list in one go. then I can type x square brackets 2 colon. Okay, so you can read the colon as dot dot dot. So give me all the elements starting from index 2 up till the end of the list. Let's verify that this does the right thing. I'm gonna print this list that we are extracting here to the console, and you see starting from element with the value 23, we have retained all the remaining elements in our list, but we have chopped off the first 2 entries, which were 17 and 19. If I want to go from the element with index 2 up to the element with, say, index 7, I can type x square brackets 2 colon 8. Now, why do I have to type 8? Well, again, because in Python everything is 0 based. The last element, when we specify a range, is not included in that range. Recall this was the same for the range function. If you type range 1, 5, counting will actually stop at 4 because 5 is not included. And we have a very similar situation here. 8 will not be included in the index set. So if we want the elements up to index 7, then this is exactly the right thing we need to type. And you see that we get 6 elements starting with the element of index 2 as intended. Okay, this is the slice operator. We can do more fancy things with it. Let's say I want only every other element starting with the one at index position 2. I can type 2 colon 8 colon 2. So this will now start counting indices at 2 going up to 8 without including 8 in steps of 2. Okay, and you see that we get 23, which is element with index 2. But the next one is 31 because we have skipped 29, and then we get 41 because we have skipped 37. Okay. That's fine. You can also go backwards, so we can go in steps of -1, thereby getting a partial reversal of the list. And if we only want to get every element having an even index of the whole list, then we can completely omit the indices, the start and the end indices, and just type colon colon 2. This would now return all the elements in our list having an even index. And if I want the ones with an odd index, of course, I should start counting at 1. And what I have to type here is indicated there. It is very easy to change the elements of a list after we have created it, as is indicated with this example here. Let's say I have this list of 5 elements. I can then change the element at index position, let's say 3 to 13, by using this notation here. Right? X square bracket 3 is assigned the value of 13, so this will change the value 29 to 13 in our list. I can change the last entry of my list by typing x square bracket -1 and assigning another value to that if I want it. Or I can change a whole portion of the list by another list. So if I type something like x square bracket 1 colon 3, I'm addressing the elements with indices 1 and 2. If I now assign to these elements a new list with these 4 elements, what I'm effectively doing is I'm replacing 19 and 13 by 4 numbers 2, 3, 5, 7. I can also clear a list, so remove all its elements, thereby obtaining an empty list by using this notation here. Access every element using x square bracket colon and assign to it the empty list. Okay. After this, you will end up with an empty list. Now here is a very important warning that causes a lot of confusion usually. If we have a list x in memory and we simply type y equal x, so in other words we assign x to y, then this actually becomes the same list as x. Y and x will refer to the same list in our computer's memory. If I want to make a copy of a list, I have to type z is assigned the value of x square bracket colon. Okay. These two lead to completely different things. In this case, in your computer's memory, you have just one list, whereas in this case, you now have a copy of the list that you started with. So you have 2 lists in memory. In order to demonstrate the difference, let me run this short Python code. Just to go through step by step, we start with the list X that has 3 elements, 17, 19, 23. And now I have these two different ways of creating lists Y and X. The first one is just assigning X to Y. And the second way is take X square bracket colon and assign this to Z. Okay. I'm going to print out the values of X, Y, and Z before doing any further changes. But then I will modify the entry in Y with index 1 to be 13. And I will modify the entry with index 2 in Z to be 11. And then we're gonna be able to look at the values of X, Y, and Z after this change. Let's do this. Okay, and let's carefully look what we have here in the console. These are the lists X, Y, and Z before we did any changes, and as you can see, and as you would expect, they all have the same values, 17, 19, 23. But now look what happened here. So after we have modified the entry in the list Y having index 1 to 13, we can clearly see this change here, but at the same time the value in the original list X has been changed to 13. Okay, so changing a value in Y, which we have created as a copy like this, has affected the value in X as well. This could be kind of unexpected, right? You would think that, well, is Y not like it's a list on its own sake, like completely independent? No, it isn't actually. When you modify Y, you also modify X. Whereas the modification of the last entry in Z to 11 has only affected the list Z, not the other lists X or Y. And that's because we have created Z as in a different manner than we have created the list Y. This notation X square bracket colon produces what is called a shallow copy. Okay. You can also do this by typing x.copy, so calling the copy function for the list X. It is not exactly what one would consider a deep copy. It's just a shallow copy. You can read more about this in the online documentation linked here. But what is very important now for us is that this behavior of list changes affecting copies of the same list, we need to be very careful when we give lists as input arguments to functions. So here is an example that demonstrates this. I'm defining a function f, which takes 3 input parameters a, b, and c. And the function does nothing really exciting. It basically just assigns the value 19 to the variable a. It assigns a list with 3 elements to the variable b. And it assigns the value 11 to the element with index 0 in C. Right? These are the 3 input arguments. Now what I define here outside my function are 3 variables. X is just an integer and 2 lists Y and Z. Okay. Again, we are going to print out the initial values of X, Y, and Z, and then we call the function with these input parameters. Now remember what we have learned before when we talked about functions. The variables that you hand over to a function are going to be copied. And when you do any modifications of these variables inside your function, they actually stay retained in that black box, right? So you don't need to worry too much about changing an integer variable within your function. It will not affect an integer variable by the same name outside that function. Now this is no longer true when we work with compound data types like lists. Okay. And to illustrate this, let me execute this in Spider. And what we see here is that after I have called my function with input parameters x, y, and z, the first element in my list z has been changed from 29 to 11, right? Even though my list z is defined outside that function. Okay, so this is unexpected. You would not think that your list is modified inside a function and that this modification would affect any variables outside your function, but that's exactly what happened here. So why does Python treat lists in this particular manner? Why are functions allowed to change the elements of a list that are given to it as input parameters from the outside? Now, in order to motivate this, why have the Python developers decided that this is how lists should be treated? I would like to briefly explain how data is organized in our computer's memory. Okay. In a very abstract sense, you can think of your computer's memory as a string of cells that can store data. Okay, you have a very long string of cells. On the very fine level, in each of these cells, you would have zeros and ones. Okay, so-called binary code. But for the sake of this demonstration, let me just assume that in each of these cells, we can store exactly one number. Okay, so I have maybe number 17 stored here. I have number 23 stored here, 9, and so on. So each of these cells stores one of these values in our computer's memory. And that's exactly what we would refer to as a list, right? So a list has an element with index 0, let's say, an element with index 1, and so on. And maybe this list has, let's say, 100 elements or 101 elements, then the last index would be 100 here. Okay, so my last entry maybe is -3. Now this is a list. However, the way you should think of a Python list X, which we define using square brackets, is not as this collection of 101 numbers. You should rather think of X as a pointer to the first position in your list. Okay, so think of X as a pointer to the first element. Okay, so when you type in Python y is assigned the value of x, what you really do is you are copying this pointer to the position of the first element in your list instead of actually creating a copy, right? So this here will now point exactly to the same position in your computer's memory. So when you then type in Python, change the element with, let's say, index 1 to 8, right? Then what this really does is it changes this 23 to 8, and because x points exactly to the same list in your computer's memory, this change would affect both x and y. Okay. If you type z is x square brackets colon, then what Python does is it goes through this list from left to right, because that's exactly what this square bracket colon operator does. It basically lists all the elements one after the other, and it thereby creates a new list, which is then assigned to z. So this operation here would copy 17, 8, 9, and so on, the elements that we have in our original list, and create a new pointer, z, which points to the first element in that list, right? Therefore, any changes that we do to z do not actually affect anything that is being referred to by x and y. Right, so this is interesting. And why is this useful in practice? Well, your computer's memory is basically what your computer is working with when it stores information. And this process of copying data, like creating a copy of a list, actually is computationally intensive if you have a very long list. Furthermore, if you have a very big list with, let's say, lots of strings, and maybe you're storing all the phone numbers of people having a phone in the UK, let's say, right? You can imagine there is a very long list and a lot of data to store. If every time you want to operate on this list, you would create a copy first, that could slow down your computer dramatically, and it would also basically exhaust your computer's memory. Okay, so we typically want to avoid creating copies of long lists, and that's why the default behavior in Python is to not create a copy, but to just copy the pointer to the beginning of that list. If you keep this in mind, I think it would avoid some of the confusion that would otherwise occur. Sometimes we want to work out what is the length of a list, like how many elements it has, and that's easy enough. We just type len x, where x is the corresponding variable for the list, and it will return an integer value corresponding to the length of that list. If the list is empty, the length will be 0. In the lecture notes, you will now find a very long list of functions and operations that can be performed on lists. It makes no sense for me to go through these in detail. You should really work your way through them independently. I would therefore just be very brief in what follows. What I would recommend you to do is to create a summary of the lecture notes, where you just pick out the commands that can be operated on using lists and write them down in a concise manner. For example, there is a function you can call called append. Okay, so the list is x still, and you can type dot append, which takes an input parameter and it basically appends this element to the list. It can only be called with one input, so here would be the correct syntax. So let's say I have this list x here. This is how I change one element of that list. If I want to append an element, I can type x dot append. Yeah. If you want to join two lists together, you can use the plus operator. So if I type this in Python, it would create a list with 5 elements, 1, 2, 3, and 4, 5. If one wants to add more than one element, so this by the way only works for one element. If one wants to append more than one element, one needs to use the function extend. So extend. The extend function takes an input element which is another list, so it would be a list like this, and would then append these elements one after the other at the end of your list, right? And so on. There is another command called insert, which takes a position, let's say 0, and an element, and it will insert this element, in this case 13, at position indicated by the first input argument, which is 0 here. It is also possible to insert elements using the slicing operator. So if I type something like this, it would address the element at position 2, but it would not substitute it because the end index is always one larger than it is actually addressed to. So this here is in fact an empty list starting at position 0, and we are going to replace this by another list 3, 4. So this would effectively insert the list 3, 4 at the position 2 of our list. And so on. You see, what I'm alluding to here is that there are many operations and you really need to play with them yourself in order to fully appreciate what is possible in Python. And in order for you to do this effectively, I really recommend making a short list of all these commands that are available. I had already mentioned early on that the elements in a list can be of different types, so we can have a mix of integers, floating point numbers, and so on. We can even have lists whose entries are lists again. Okay, so like in this case where we have a list with 3 elements, 17, 1.7, and then another element which turns out to be a list. Okay. The length of this list is of course 3. There are only 3 elements because this here counts as a single element. And if I want to access this element, I can type x2, which returns me that list. Of course, I can also directly get this element 29 by asking for x2 square bracket 1. So this will extract the element at index 2, which is a list with 2 elements, and this will return the element at index 1 in that list. So we should now see 29 being extracted. Of course, this does not work for the other list elements of x, so I cannot, for example, ask for the second element of x1 because this floating point number 1.7 is not subscriptable, and we get an appropriate error message here. It is possible, of course, to reverse the order of a list, like to go from the back to the beginning. And here's an example that illustrates this using the reversed function. I just want to show you what happens in Spider. So let's say I have a list with some elements, and I now want to reverse that list. I can call the reversed function. And what you actually get is not a list. You see, it outputs something strange. It says list underscore reverse iterator. So the reversed function does not itself return a list. If I want a list, I have to explicitly convert the return value of reversed to a list, like so. And there you have it. This is now a list that has the same elements but in reversed order. So what is this reversed actually returning? It is an iterator. Okay. If we go back to our picture here, you remember that we have, let's say, a list with 101 elements in our computer's memory. Now imagine a situation that you just want to go from the last element to the first. You have some kind of for loop and you want to start going through all these elements one after the other, starting from the last one. Do you actually need to first create a reversed copy of this list in your computer's memory? Or can you do this in a more clever way? Well, all you need in order to go through this list is the beginning of that list, which is here, and the instruction to go backwards one step at a time, right? This is all you need in order to reverse that list or to access the elements of that list in reversed order. And that's why in Python there's a difference between in-place reversal, which reverses list elements without creating a copy, making a copy of the reversed list, and just returning an iterator that gives you the elements of a list in reversed order. This is explained in more detail in the lecture notes. Basically what it means is you can take the output of the reversed function and put it inside a for loop, right? So you can type something like this: for I in reversed x. That's a for loop, colon, print I. If x is a list, I would now contain all the values of the original list, but they would be traversed in reversed order. So you see 53 is the last element of our list, 47 is the second but last, and so on. Now, if I want to make a copy of a list and reverse it, then I can do that, but of course I would then have two lists in my computer's memory, and if the original list is very large, then that's not a good thing to do. Okay. So-called in-place reversal refers to a procedure where you swap the elements directly in your computer's memory. So if you want to reverse this list without creating a copy, you just need to swap 17 with -3. You would have to swap this element with whatever is here, and so on, right? So this would be in-place reversal. And in Python, this is done with calling the list name dot and then the function reverse. Okay, that's the in-place reversal function. It is easy enough in Python to sort the elements of a list by using the sorted function. So let me just demonstrate this here. I have a list X with some integer elements. I can just create a sorted copy of this list X and assign it to, let's say, a variable Y, and then print it out. And as you will see, that this returns another list, a new list, which has the same elements, but in the order is now ascending. If I want decreasing order, I can give another input parameter to the sorted function, which takes a Boolean value, reverse true, and now we have that same list, but sorted in descending manner. This here, by the way, is a good example of a named argument, as we have discussed in the functions lecture last week, right? So I need to call this as a named input argument for the sorted function. Now another interesting possibility is to call the sorted function with a sort key. So that's another input parameter that is named. And I just show you an example what this actually is. So let me define a lambda function, right? Recall the concept of a lambda function, a function that takes only a certain set of input parameters and returns just one value. So that's a very short way of defining a function. I will define a lambda function that takes as input parameter, let's say t, and it just returns minus t. If I now call this, then this will have the same effect as sorting with the reverse true option. So what is this key? This sort key basically helps Python to determine the value of an element in your list by which it has to be sorted. So I can look at the original values of my list 17, 13, 19, 11, 23 and so on and sort them in, let's say, ascending order, or I can apply a function to each of these elements first. So if I apply this lambda function, which just negates the sign, to each of these elements, I will have a list that looks like minus 17, minus 13, minus 19, and so on, and then sorted in ascending manner. Well, that's the same as sorting the original list in descending manner. So this key here, just think of it as a function that is applied to each of these elements before sorting the list. And we will sort by the function value that is being returned by this key function. Now this is very interesting because we can now sort lists in all sorts of strange manners. For example, I can sort by the sum of the digits of the numbers in that list. So let me just copy and paste our digit sum function that we have discussed in some previous lectures. Let me just copy and paste that function here. And as our key, I will now use digit sum. Okay. So basically what happens now when we ask Python to sort that list here, it will basically evaluate digit sum for each of these integers here. It will compute essentially the sum of the digits and then sort this new list by the sum of these digits. Okay, so let's see what we get. Okay, we get now 11, 13, 23, 17, and 19, and you will find that this is now indeed ordered ascendingly by sum of digits. And I can combine this with the reverse option as well. This will be the list in reversed order by the sum of digits. I think this is a good application of named arguments and also how to use lambda functions. Let me also highlight that the sorted function creates a copy of the original list in your computer's memory. There is an alternative way of doing in-place sorting using the sort function. If you just have a list X and you type x.sort brackets, then this calls in-place sorting. So it will basically bring the elements in the correct order without creating a copy of that list. Now I will just add these things that we just discussed to my logbook here. So what have we done so far? We have learned about the reversed function, which does not return a list. It actually returns an iterator. So we need to explicitly convert it to a list, or we can do in-place reversal by calling the reverse function on a list. And likewise, there is a sorted function x that can take also a reverse equal true named parameter, or a key, which could be a lambda function, let's say. And likewise, there is in-place sorting, which is called like that. So that would be in place. Okay, so please go through the lecture notes, play with these functions, and make sure that you understand the difference between these options. So this here actually doesn't return a list, it returns an iterator, but you can convert it to a list, by which you then actually have two lists in memory, whereas here you're working on the same list. And likewise for the sorted function. If I want to find out whether a certain element exists in a list, I can use the in keyword. So here we have a list lst, Recall, I didn't call this list itself because list is a reserved keyword. And if I wanted to find out whether, for example, the element 17 is in that list, I can type 17 in LST, and you already guessed it, the return value of this operation will be a Boolean value, either true or false, and in this case it is true. So using this, I can now do things like this. If 17 is in list, print hooray. Okay, and it should work. Yes, 17 is in the list. If I change this to 7, say, then of course it won't print out hooray because 7 is not a list element. There's also a function that returns the index of a given element in a list. It's called the index function. So if you type your list name dot index and then you give it as an argument an element of your list, it will return the integer position corresponding to the first occurrence of that element in the list. So you see that x index 17 returns 0 because 17 appears at index 0. But this method actually fails if you ask for an index of an element that does not occur in the list. The Python interpreter will return a value error here. So before using that index function, we first need to check whether the element actually exists in the list. One can also count the number of occurrences of an element using the count function itself. Okay, and in the lecture notes you will find plenty of examples where the in, count, and index function are illustrated. So please have a good look at these. We can of course write our own function that finds a given element in a list. I have an example here. So this function is called find. It takes as input argument a list L and another variable x, which will be the element that we are looking for. And you can already see in the docstring, this function returns the index of x in L, or it returns none if x does not exist in L. And how do we implement this? Well, in order to check whether an element exists in a list, we really have to go through the list starting at the beginning and looking at each element one after the other, right? So that immediately means that, well, we need a for loop. So how can we loop over the elements of a list? It turns out that in Python this is very easy. You can just write a for loop like this, for L in L. So L is my variable which will hold the element that I'm currently looking at. L is the list that I have defined here. You see I'm calling this function, this find function, with my index parameter, with the list parameter being x, which is defined here. So you can just have a for loop of that type. And now once we have this particular element, for example the first one, we just need to check, is this element the one that we are looking for? Is this element equivalent to x? If it is, then we are happy. We will just return the corresponding index. Now the first index will be 0. If we are lucky enough to find the element at position 0, we will return here in the first iteration. Otherwise we have to continue our loop, so we have to increase I by 1. So that's a nice example where we have a for loop over a list. This for loop will go through all the list elements until it actually finds the value x that we're looking for, and it will then return. Remember that the execution of this function will immediately stop when we encounter return. So if we find the element at position, let's say 3, we will not have to look at all the remaining elements of that list. If this for loop comes to an end because we have traversed all the list elements without this return being evoked, right? Then that clearly means that the element is not present in the list, in which case we return none. Okay? So that's a simple example of so-called sequential or linear search. Now here's a slightly more sophisticated example, which will use a function called isPrime, defined here. This is a function that returns true or false depending on whether the input argument n is a prime number. Please have a careful look at this example. How do we check whether a given integer is prime? Well, it's fairly straightforward. If the integer that is being entered is less than 2, then we are sure this is not a prime number, right? It would even work for negative numbers. If you ask whether -7 is a prime number, this function would just return false. Now, if this is not the case, if n is 2 or greater, then we need to check whether this function is divisible by some integer less than that given number. So what we do here is we really check every integer, starting with 2 going up to n-1, and we are verifying whether n is actually divisible by that integer I. It is divisible if this division here returns 0. If we find such an integer I, then we return false. If we come to an end of this for loop without returning false, we haven't found any integer I so that n is divisible by I. Therefore, we are sure we have a prime number. We will only reach this final line of the function if that happens, in which case we are sure that n was indeed a prime number. Okay. So this is a nice function that you can also use in some of the exercises for this week and the following weeks. You can just copy and paste it, but please make sure that you understand how it works. This function verifies if a given integer is prime. By the way, there is a more Pythonic way, so you can do this in a much shorter manner, as shown here. We will understand later on in the course where this notation comes from. At the moment it looks a bit scary, but in fact this code here is completely equivalent to this here. Now we can use this isPrime function, for example, to find whether a list contains prime numbers, or in this case to print all the elements of a list which are prime numbers. So let me copy and paste this into a Spider, and let's discuss it briefly. So we have a list LST that has elements shown here, and what we want to do now is to just print all the elements which are prime. We have a for loop over this list, so this will take one element at a time from the given list, and then we have a if statement here checking whether that particular x is prime. If it is, we print it out to the command line. Now you see already in Spider there is an indication that I have a problem here. By the way, it's always very good to keep an eye on the left side of your editor because it gives you very valuable information about your code. It seems that I have not defined isPrime. Of course, I need to copy and paste the isPrime function as well in order to use it. So let me just do that. I'm gonna put that here, and now we'll find that this complaint here disappears and this code will now run. So let's see what we get as outputs. Okay, we have found prime numbers 13, 17, 2. This number happens to be a prime number as well, and 19. And you might have noticed that verifying whether this number or this number, I don't know which one was the problem here, probably this one, is a prime number takes quite long. Why is that? Well, if you look at our isPrime function, it actually checks all the integers up to n-1 for divisibility, right? So this can become very expensive, and that's exactly what you see here. A computer takes some time to go through all the possible divisors of this rather large number here. If instead I wanted to print all the indices of the prime numbers in that list, I could do something like this. I have now a for loop for the indices, and how many indices do I need? Well, I need to start from 0 up to the length of that list -1, so that's exactly obtained by using range length of the list here. And I'm now doing the same check, isPrime, but now I is the index, no longer the element. So in order to get the corresponding element, I type LST square brackets I, and then I print out the index if I'm lucky enough to find a prime number. So let's run that. And what we'll see is that there is a prime number at index 1, 3, 7, 9, and 10 in this list. And of course, there's always a more elegant way to get both the index and the element at the same time using a function called Enumerate. Let me copy and paste this. So if you do a for loop with enumerate on the right side of the in keyword, then this returns a pair of an index and the corresponding element. So you get both the index and the value of that element at the same time. And what we now have here in X is the corresponding prime number, so I can print it out separated by comma at index and then followed by the index of the particular element. For example, the number 2, which appears as an element in our list, is a prime number, and it appears at index 7 in our list. So just to recall, the enumerate function can be useful if you want both the index and the list element at the same time. Let's briefly recall the many keywords that we have learned so far. I still have my list here, so I'm gonna add these. We have learned about the in keyword, right, which can be used to check whether an element appears in a list. So I can type L in LST, where LST is the list name, and this will return true or false, depending on whether or not the element EL is a member of that list. We have learned about the index and count functions, which can be called on any list with a certain element, okay, like so. And what they do is they return the index of the first occurrence of the element EL in a list X, or they count the number of appearances or occurrences of an element in a list X. With these functions, one needs to be careful that EL is indeed an element in that list, and we can use the in keyword for checking this first. We have seen how to iterate over list elements, so I can type for loops like that, for element in LST, for example, and then I could, for example, print the corresponding element. So you can just loop over the elements of a list like so. And we have learned about the enumerate function that returns pairs of indices and elements. So inside a for loop, you can use them very conveniently to get both the index of an element and the element value. I think my list does not yet contain the function len, which we use for checking the length of a list, right? So that's quite a useful command. The lecture notes contain a couple of exercises which are straightforward modifications of the examples that we have discussed already. So please have a go at these. And there is a bit of write-up about inputting a list. How would you ask the user to input a list? Well, you would probably start with an empty list, okay? And then you have some kind of loop, either a for loop or a while loop, where you ask element by element for the user to input the corresponding value, and then you just append it to a growing list, right? And then there are different ways of stopping. You might agree that you first ask the user how many elements do you want to input, maybe 5, then you can do a for loop because you know that you want to ask for 5 elements. Or you could agree that as soon as the user enters -17, the input procedure stops, in which case you would probably want to use a while loop. So these situations are discussed in the lecture notes as well. Just a few more words about deleting elements from a list. Okay, it is possible to use the slicing operator for doing so. Let's have a look at our list that is still in memory. Let's say I want to delete a certain element from this list. How would I do that? One way is to use slicing operations by addressing that element and assigning an empty set to it. Right? So for example, if I type list 3:4, what this refers to is a sublist of the original list containing the element with index 3. So 0, 1, 2, 3. So that would be the 17. So that's a list, right? Because it's a sublist. It just has one element. If I reduce this list to the empty list, I'm effectively removing 17 from my list. So let's print this. And you see that 17 is missing, right? And likewise, I can remove more than one element. If I want, for example, I can remove all the elements starting from the one with index 3, like so. So that's rather straightforward. There is a more explicit way in Python with the del keyword. So you can just type del and then specifying the positions that you want to delete. And that is typically a more explicit way of doing things, and is slightly preferred because when you read the code, you see explicitly, here, someone is actually deleting elements from a list. It's very clear, but it's technically the same as using this notation here. So it's up to you which one you prefer. Now, to wrap it all up, for you to practice inputting data from the user, like asking for list elements, and to do some computations on lists, there is an example in the lecture notes that I would like you to work through independently. It's a program that loads integers from the user, so they will input one integer at a time until it loads a 0. This 0 should be excluded from any following computations, and then computes the arithmetic mean of all the loaded numbers, the median of all the loaded numbers, and also prints out the loaded numbers that are bigger than or equal to the median in their original order. Right? So inputting some data from the user and doing some computations and outputting the result. That's what this exercise is about. Now, you don't actually need to write it yourself. You might have a go first to write this program yourself, but the solution is already given to you. What I would like you to do is to go through this example step by step and see that you fully understand it. Right? There's nothing in here that we haven't discussed yet, so hopefully it should be fairly easy for you to make sense of this slightly longer computer program. And as before, I provide different versions, so there is a more Pythonic solution which is much shorter than the original code, but you would not be expected to write a compact code immediately, just having started with the course, just for you to see what can be done in Python. Okay, lists are only one type of Python's iterables, which are objects that contain some member elements that can be accessed one at a time. Basically, you know that you're dealing with an iterable if you can put it in a for loop. So a variable var is an iterable if you can use it within a for loop, like so, getting one element at a time using for element in var, right? So that's the kind of, you can think of a iterable definition of this type. Now, we will discuss a short preview of some of the other iterables that exist in Python. The first type I would like to discuss are tuples. Tuples are basically an immutable, which means unchangeable type of list. Okay, they can be assigned a new value like any variable, but you can actually not change its elements. Okay. Tuples are defined using round brackets or using the tuple keyword, like so. So this would define an empty tuple, and this would also be a tuple, but this notation is of course slightly less preferred because it can be confusing, right? It could be confused with something else. And this is yet another tuple that is being defined here. So let me just try this out in Spider. This is the definition of a variable called a tuple, which has 4 elements. Okay, you can see its size is 4, and some of the list functions work just as before. So for example, I can ask for the length of this tuple using the len function. It will be 4, and I will, however, not be allowed to change any of its elements. Okay, so for example, this assignment here will not work. And the error message that I get is that tuple object does not support item assignment. Right? I can retrieve the, let's say, second element of this tuple just as I could do with lists. So this would be valid. Just need to print out the result like so. Okay, which is 19, but I'm not allowed to actually change the list element. So you might wonder, well, okay, if a tuple is basically like a list, but it can just do fewer things, then what's the point? What's the purpose of it? The reason for tuples is that we use them usually in conjunction with function returns. Remember when we were writing our function, we were able to return a certain value, but we can use tuples to return more than one value. So here is a simple function, call it myFun, and it will return a value. And let's say I want to return actually 2 values, x and y. So I have 2 variables that I have computed. one way to return both of them at the same time is to do this. And that actually turns out to be just the definition of a tuple with the brackets omitted. Okay, so if I call this function and I print the result, and it turns out that the result that is being returned here is a tuple. Okay, so that's the real use of tuples, because we know in advance how many elements will be returned. Tuples are not as flexible as lists. We can rely on the fact that this function will always return a tuple with 2 elements. Now the nice thing is that you can use tuples in an intuitive way to get the elements one at a time. So if I want to get the variable output x and I want to assign it in my variable a, and likewise I want to assign the return value y to my variable b, I can type this in Python. Okay, so after this has been executed, I have the value of 7 in a and the value of 2 in b. So it is perfectly fine to have an assignment where on both sides you have a tuple and the values are assigned respectively. In other words, it is also allowed to do something like this. Okay, what this does is it assigns the value of 4 to x and the value of 2 to y. And of course, this is different from doing this here, right? This will assign the value for 2, which itself is a tuple, to the variable 2. If you want to define a tuple that has just one element, then this will not do the trick, right? This will actually define an integer variable because it's basically just an integer number with some brackets. If you want this to be a tuple with just one element, you need to add a comma here. And you see now x is indeed a tuple. Now, when we were discussing lists, we already mentioned that it is sometimes required to get both the index and the value of a list element. And the inconvenient way of doing it was to have a range command over the length of the list. And then the index, of course, is what the range command is returning. And the value of the list element would be li. And then we had seen that a much more convenient way of doing so was the enumerate function, right? So I can just write a for loop where I get a pair of values as my variables, then the in keyword followed by enumerate of the list. So now we actually understand what this notation here is. This idx, L is in fact a tuple assignment. And we can see this very clearly by running this example here. We have a list of 3 elements, and what I'm going to output now is the return value of enumerate L. What does enumerate L actually return? Well, it returns an iterator itself. So in order to convert it to a list, I need to do it explicitly like so, and then print out. And what you see here in the console is that enumerate L returns, after conversion to a list, 3 tuples, and the tuples consist exactly of the indices 0, 1, 2, followed by the list elements 17, 19, 23. So what happens when you put this into a for loop? In the for loop you would get one tuple at a time from the enumerate function and assign it to an idx, L pair, like in this example here. So really what we have here is really a tuple assignment in disguise. Another data type in Python which can be iterated over are sets. A set is like a list in which all the elements are unique and they have no predefined ordering. Hence, we cannot really index the elements of a set. There are implementations of standard set operations. We can check membership in sets just as we can do with lists and tuples. So I can be very brief here. The way sets are defined is via curly brackets. So you see some examples here. Here's a set A with elements 17, 13, 19, 23, so 4 elements, and a set B. And once you have 2 sets in memory, you can, for example, compute the union. So you take the first set, dot union, and then the second set in brackets. Okay, so this would compute the union of both sets. It should be emphasized that the empty set in Python is defined using the set function, right? This here is not an empty set. It's something different. It's a dictionary that we will discuss next. We will use sets quite rarely. I think the most common use of sets is if you have a list and you want to get rid of duplicate elements in that list, then a convenient way of doing this is to first convert it to a set. So to show you an example in Spider, here is a list that has elements 17, 19, 23, and let's say there are some duplicates. So maybe 17 and 19 appear multiple times, right? So let's print this list on the command line. Then I can convert this list into a set by typing this here. So the set function also accepts a list as an input, and it will return a set. So let's call this a set. And just to confirm what we have done here, let me print this out. So this is now a set that has been generated from the list L, and you see that the ordering is a bit messed up, and also all the duplicate elements have disappeared. And if I now take this set and I convert it back to a list using the list function that we have seen before, and then I print out this list, then what we have effectively done after all is we have taken the original list and we have removed all the duplicate elements. I think this is one of the most common use cases for sets. Otherwise, they are quite rarely found in Python. The final data type that we discussed today are dictionaries. Dictionaries are a very powerful data type in Python, and they are in some sense very similar to lists, except that they do not have integer-based indices like 0, 1, 2, 3, and so on for their elements, but they use keys. And as keys, we can pretty much use any immutable data type. It could be integers, as in lists, but we could use floating point numbers, we could use strings, and so on. Right? Even tuples can be allowed as keys in dictionaries. The way dictionaries are defined is using the dict function, as is shown here. It takes a list of input arguments, which are essentially, you can think of them, named parameters. So this here defines a dictionary that has 3 entries, 1, 2, 3 as integer values, and the corresponding keys are given here, 1, 2, 3. These would now be string keys. An alternative way, one that I slightly prefer, I'd say, is using curly brackets. So this here defines the same dictionary using a different notation, and you see that the key value pairs are separated by colons. What is in front of the colon is the key, and what follows the colon is the value. So the values are integers 1, 2, 3, and the keys are strings 1, 2, 3. Okay, so it is sufficient to remember these two ways of defining dictionaries. And now you see why the empty curly brackets do not actually define a set. If you just keep these empty, then you would actually define an empty dictionary. Alternatively, you could also do it in this way, just calling the dict function without any input arguments. Now, in order to understand precisely what is the use of dictionaries and also to motivate their name, let me define an English-German dictionary as follows. I call it en_ger, for German. And what I want to do is, as keys, I want to use English words, and as corresponding values, I want to use a German translation. So let's use as a key maybe the word sun. Okay, and the corresponding translation into German would be Sonne. Right. So that's my first entry in my dictionary. It's a key value pair. Let's add a few more words. Let's say the word for car. The German translation of this would be Auto. And finally, maybe the sea. The German translation of which would be das Meer. Right? So that defines a dictionary with 3 entries. And the way I can now use this, the way I can access the elements of that dictionary is just as with lists, using curly brackets. So if I wanted to get the German translation of the word sun, I can type dictionary, square brackets, and then I have to call the key, which in this case would be the string sun. And if I print this out, I will indeed get the translation of that particular word. Right? So you see, it's very similar to a list. A list could be, for example, defined as follows. I could have keys which are integers 0, 1, and 2. So that's still a dictionary, but it would pretty much behave like a list, right? I could access the elements by their index. But the point of a dictionary is that we do not need to do this. We can actually use strings as keys in a dictionary. In fact, you can even use tuples as the keys in a dictionary. Now, because dictionaries are iterables, we can iterate over them using the for keyword, okay, as we have seen before. So let's test this out in Spider using our English-German dictionary. We have a for loop. We get all the keys from our dictionary, which is now called English-German, and then we print out the key and the corresponding value. Let's run this. And as you can see, we are now producing exactly the key value pairs as we have listed in our dictionary. If we want to get both the keys and the values at the same time, there's something similar to the enumerate function for lists. Of course, it makes no sense to enumerate the entries of a dictionary because there is no natural order, right? Remember, the keys are arbitrary. They can be any immutable data type. So there is not necessarily a particular order that these keys are stored. Therefore, the corresponding function in Python is not called enumerate, but called items. And that's the syntax we would use. You take your dictionary variable and then you say .items brackets, and this returns, as before, a list of key value pairs as a tuple, and then we can use them within our for loop. So that's a more convenient way to traverse this dictionary and print out all the entries. And it's also possible to sort the output by the key values using the sorted function that we have learned about earlier today. So if I just wrap this items function inside the sorted keyword, then what I'll get is the dictionary printed, but now in alphabetical order according to the key values, just like a real dictionary. There are various ways to print a dictionary. Of course, we can just call print and then the dictionary name, but as this following example demonstrates, this can look very messy. So I have here a dictionary that is rather messy. You see, it has a mix of keys, which are strings, and I have here an integer value and a tuple. And look, the values of the dictionary can be anything. It could be like strings, integers. Here I have a list as a value that contains as one of its elements another list, which is a mix of integers and strings. So basically everything is possible. And if you try to look at the output after print on the command line, you see that this is very hard to decipher, right? It's very difficult to make sense of. Therefore, Python has a function called pprint, which stands for pretty print. And it can be used as follows. One needs to import the preprint function from the pprint module, and then it can be called in this way here. So let's see how the output looks like when being called on this particular dictionary. It's just more readable. You see, these are the entries and they're nicely spaced out, and also every key value pair is printed on a separate line. So that's easier to read. Notice, however, that the ordering of the keys is completely arbitrary. Just like with a set, you cannot really rely on the ordering of the entries in a dictionary. There's no natural ordering. In particular, the way we have specified the orders is of course not represented in memory, and therefore also not necessarily printed out on the console. Another thing to notice is that we have actually used the same key when defining this dictionary twice. Right? XYZ is a string that has first been assigned the value something, which is a string. And then in the second round, we have assigned the value something else. Now, of course, the keys in a dictionary need to be unique. Otherwise, how can we address the elements in a unique manner? So what happened here is when I reused the key XYZ for the second time, the previous one got overwritten, right? So you can have only one use of a key inside a dictionary. You see that only something else has been retained, whereas the string something is lost. Now this also brings us to the question of how do we change the entries in a dictionary? Well, that's just as with list elements, using again the square bracket operator. Let's say I want to change the value of the key 2, which is a string. I can of course just type d square brackets string 2 is 2020 and then print out this dictionary. Now again using the bad notation, but hopefully we will see that the key 2 now has a value of 2020, right? So I have just changed an entry in my dictionary, addressing it by its string key. Likewise, I can of course change, for example, the entry that has key, which is a tuple 10. Okay, I'll do this, and maybe this will become a list having just one element. 9, completely valid. Here you see the change has been carried out. Adding and deleting data is also straightforward. Let's go back to our dictionary D. If I want to add a certain key to my dictionary, I just define it like so. So I can just say d square bracket, and then I list a new key and I assign a new value using the assignment operator. So this would add a new key to our dictionary. If I wanted to change an element in my dictionary, I can do this again with an assignment. If the key already exists in my dictionary, which is the case here, then the corresponding value will be changed. And finally, if I want to delete an entry in our dictionary, then I just use the del keyword and I address the corresponding element again by its key. So this here would delete 2 elements from our dictionary, the one with key tuple 10 and key XYZ as a string. Already mentioned before, we can use dictionaries with the for keyword. We can just say for x in D, which will return the keys of our dictionary. And likewise, if I wanted to also access the values, I could do that by using again the square brackets. Okay, so once I have the key x, I can access the element or the value corresponding to that key using the square brackets notation. And as we have already seen before, the items function, when operated with a dictionary, returns tuples, which are key value pairs, just as the enumerate function does for lists. Okay, finally, it would be convenient to be able to convert between lists, tuples, and sets in a manner that is kind of going back and forth between these data types. And that's indeed quite easy. So it is quite easy to convert a list into a tuple by just using the tuple function. Likewise, we can convert a list to a set by using the set function. And this works in all directions. So if you're given a tuple, you can convert it to a list using the list function or to a set. And if you're given a set, you can convert it to a list or a tuple. Of course, because in sets, the order of the elements is not necessarily specified. So when you convert a set into a list or a tuple, you get more or less a random order. You can't really rely on the order of the elements. Finally, let me also mention that it's possible to create dictionaries from 2 lists, so or maybe a list and a tuple, as is shown here. I have a list called keys, which has some entries, and I have a tuple called values, which has some elements. Then I can use the so-called zip function. Okay, zip takes 2 inputs, which are of the same length. They could be lists or tuples, and it basically pairs them up element by element. So the first element in keys will be paired up with the first element in values to create the first entry in the dictionary, and so on. Right? So that's a convenient way. And of course it's called zip because it's like a zipper, right? So you have maybe 4 elements here and 4 elements here, and with the zip function you just bring them together like a zipper. Now, just to wrap up this lecture, I just mention again that I think it would be very useful if you create your own summary of the most important keywords and commands and functions that you have learned, not just in this lecture, but actually in all the follow-up lectures. You have already seen this. We talked about lists, how to reverse them, how to sort them, how to check whether an entry is contained in that list, and how to iterate over a list. The reason why we can put lists into for loops is because they are iterables. And then we have talked about some other iterables in Python. Most notably, we have learned about tuples, okay, which are defined using braces. They are like lists, but their elements cannot be altered, right? So the tuple, once it has been defined, it can never be changed. And the most frequent use is for returns in functions, right? Because you can rely on the number of elements that you get back from a function. And we have also seen that you can do assignments like that. So you can assign 2 variables x and y in one go by using this tuple notation. And it turns out that in fact these brackets are optional, so they can be omitted. So this would be completely equivalent. What I haven't mentioned is that this is in fact a very convenient way to swap the order of 2 variables, right? So if you have a variable x and a variable y and you want to swap their values, you can do so using this tuple notation in that form. We have learned about sets, okay, which are defined using curly brackets, and we have also learned about dictionaries, which are key value pairs. So key can be, for example, a string, and then we have some form of value, in this case also a string. Okay. So dictionaries are very useful, and we will make extensive use of them. I told you how to use the pretty print function, and also the items function. So if we have a dictionary D, we can use the items function to get tuples of the keys and values in this dictionary. Finally, there are conversion functions. So we can convert, for example, a set into a list using the list function, likewise the set function, likewise the tuple function, and also likewise the dictionary function. Okay, so we can convert back and forth between these different data types. Okay, that's it for today. I hope you have learned something interesting, and please be encouraged to try out all of these things in Spider, just to get used to converting back and forth between different data types and to learn when to use what data type.